Good morning. I am Aditi, studying in BSc Chemistry Honors, first year, second semester. Today, in this video lecture, we are reading chapter Thermodynamics. General introduction. It is a well known fact that the most of the physical changes and chemical changes are accompanied and energy changes. These energy changes may take place in the form of heat, light, work, electricity, and etc. All these terms of energy are convertible into one another and hence are related to each quantitatively. The branch of science which deals with the study of different forms of energy and the quantitative relationship between them is known as a thermodynamics. When we confine our study to chemical changes and chemical substances, only the restricted of thermodynamics is known as chemical thermodynamics. The complete study of thermodynamics is based upon three generalizations called first, second, third laws of thermodynamics. These laws of thermodynamics apply only where the system is in equilibrium or moves from one equilibrium state to another equilibrium state. The laws have been arrived at pure the basis of human experience and there is no theoretical proof for any of these laws. However, the of these laws is supported by the fact that nothing contrary to these laws have been found so far. Contrary is expected. The importance of thermodynamics lies in the following fact. It helps us to predict whether any given chemical reaction can occur under the given set of it helps in predicting the extent of reaction before the equilibrium is attained. It helps to deduce some important laws like chemical law of chemical equilibrium, distribution law. The limitations of thermodynamics where it fails to give any information are as follows. It helps to predict the feasibility of a process but does not tell anything about the rate at which process takes place. It deals only with the initial and final states of a system but does not tell anything about the process. It deals up with the properties like temperature, pressure, etc. for the matter in bulk properties but does not tell anything about the individual atoms and molecules. Some basic terms and concepts. Some basic terms and concepts commonly used in thermodynamics are briefly explained below. System and surroundings. The part of the universe chosen for the thermodynamics considered the study, the effect of temperature, pressure, etc. is called a system. The remaining portion of the universe, excluding the system, is called surrounding. System and the surrounding together constitute the universe. Universe is equal to system plus surrounding. However, as the entire universe is not affected by the change taking place in the system, therefore, practical purposes, the region of space in the neighborhood of the system is taken as surroundings. A system usually consists of a definite amount of one or more substances and is separated from the surroundings by a real or imaginary boundary through which matter and energy can flow from the system to be surroundings or vice versa. Open, closed, and isolated systems. Open system. A system is said to be an open system if it can change both matter and energy with the surroundings. For example, if some water is kept in one open vessel, figure 6.1a, you can see this, or if some reaction is allowed to take place in an open vessel between a piece of marble and HCl. Figure 6.1b, exchange of both matter and energy takes place between the system and the surrounding. You can see this example of open system, water kept in open vessel and reactions taking place in an open vessel. Animals and plants are open system from the thermodynamics point of view. Closed system. If a system can exchange only energy with the surroundings but not matter, it is called a system. For example, if some water is placed in a closed metallic vessel, figure 6.2a, or if is called a closed system. For example, if some water or if some reaction is allowed to take place in a cylindrical enclosed by piston, figure 6.2b, then as in the vessel. You can see the example of closed system, water placed in a closed vessel and a reaction taking place in an enclosed cylinder. Closed, no exchange of matter between the system and the surrounding can take place. However, as the vessel has conducting walls, exchange of energy can take place between the system and the surrounding. If the reaction is exothermic, heat is given by the system to the surrounding. If the reaction endothermic, heat is given by the surrounding to the system. Further, if the reaction is accompanied by decrease in volume, mechanical work is done by the surrounding on the system, and if the reaction accompanied by the increase in volume, the mechanical work is done by the system on the surroundings. Mechanical work is also a type of energy. The movement of piston in or out also movements to an exchange of energy between the system and the surrounding. Isolated system. If a system can neither exchange matter nor energy with the surrounding, it is called an isolated system. For example, if water is placed in a vessel which is closed as well as insulated, no exchange of matter or energy can take place between the system and the surrounding. This constitutes an isolated system. You can see in this figure 6.3 an example of an isolated system. State of a system and state variables. The state of a system means the condition of the system which is described in terms of certain observable, measurable properties such as temperature, T, pressure, P, volume, V, etc. of the system. If any of these properties of the system changes, the system is said to be in different state. The state of the system changes, that is why these properties of a system are called state variables. A process is said to occur when the state of the system changes. The first and the last state of a system are called the initial state and the final state respectively. State function. A physical quantity is said to be state function if the values depends only state of the system and does not depend upon the path by which this state has been attained. For example, a person standing on the roof of a 5-storied building at a particular height has a fixed volume, potential energy irrespective of the fact whether he reached there by stairs or by a lift. Thus, the potential energy of the person in a state function. On the other hand, the work done by the legs of the person towards the same height is not same in the two cases, whether he went by lift or by stairs. Hence, work is state function instead it is sometimes called a path function. Alternatively, a physical quantity is said to be a state function if the changes in its value during process depends only upon initial state and the final state of the system and does not depend upon the route by which this change has been brought about. Example of physical quantities which are state function include pressure, volume, temperature, and energy, enthalpy, entropy, free energy, etc. As discussed later in this unit. Volume is a state function because, for example, change in volume of water in a pond is independent of the route by which water is filled, by rain or tube or by both. Similarly, temperature is a function because it does not matter how a temperature has been attained by heating or cooling. Also, the change in temperature, say from 25 degrees Celsius to 35 degrees Celsius, depends only on the initial and the final temperature and does not depend upon the route taken. Macroscopic system and macroscopic properties. Intensive and intensive properties. System contains a large number of chemical species, atoms, ions, or molecules. It is called macro system. The word macroscopic implies large quantities. Thermodynamics does not deal with the purpose of the individual atoms and molecules but deals with the matter in bulk, such properties of the macros. Systems like temperature, pressure, volume, density, melting point, boiling point, etc. are called macroscopic properties or thermodynamic properties. These are further classified into two types as follows. Extensive properties. These are those properties which depends upon the quantity of the matter contained in the system. The common examples of these properties are mass, volume, and heat capacity. Besides these, some other properties discussed later in the unit include internal energy, enthalpy, entropy, Gibbs free energy, etc. The total value of an extensive property is equal to the sum of the values for the separate parts into which the system may be divided for the sake of convenience. Intensive property. These are those properties which depends only upon the nature of the substance and are independent of the amount of the substance present in the system. The common examples of these properties are temperature, pressure, refractive index, viscosity, density, surface tension, specific heat, freezing point, boiling point, EMF of a cell, pH of a solution, mole fraction, molarity, etc. It is because pressure and temperature are intensive properties independent of the quantity of the matter present in the system that they are frequently used as variables to describe the state of a system. It is of interest to note that an extensive property may become intensive property by specifying unit amount of the substance concerned. Thus, mass and volume are extensive properties, but density and specific volume, mass per unit volume and volume per unit mass respectively, are intensive properties of the substance or the system. Similarly, heat capacity is an extensive property, but specific heat is intensive, will be discussed later. In general, ratio of two extensive properties is always intensive. In fact, any molar property is intensive property because it is the extensive property for one mole of the substance and thus become independent. To understand why volume is extensive and temperature is intensive, Intensive property: consider a closed vessel of volume V containing a gas temperature T. If a partition is put exactly the middle, each part will have a volume, but temperature will remain the same in each part. Figure 6.4. You can see the figure 6.4, a vessel containing volume V of a gas at temperature T. After partition, each part having volume V divided to T is same. Thermodynamic equilibrium. A system is said to be thermodynamic equilibrium if its macroscopic properties like temperature, pressure do not change with time. Thermodynamic process. A thermodynamic process is said to occur when the system changes from one initial state to another final state. The different processes commonly met within the study of chemical thermodynamics are as follows. Isothermal process. When a process is carried out in such a manner that the temperature remains constant throughout the process, it is called an isothermal process. Obviously, when such a process occurs, heat can flow from the system to the surroundings and vice versa in order to keep the temperature of the system constant. Adiabatic process. When a process is carried out in such a manner that no heat can flow from system to the surrounding or vice versa, the system is completely insulated from the surrounding, it is called adiabatic process. Isochoric process. It is a process during which the volume of the system is kept constant. Isobaric process. It is a process during which the pressure of the system is kept constant. Reversible and irreversible process. The various types of processes mentioned above, carried out reversible or irreversible, these terms may be understood as follows. In order to understand a reversible process, imagine a gas confined with a cylinder provided with a frictionless piston upon which is filled some very fine sand. Suppose the pressure. You can look at figure 6.5, understanding the concept of reversible process. Suppose the pressure exerted by the gas on the piston is equal to the combined pressure exerted by the weight of the piston, the pile of sand, and the atmospheric pressure. Thus, under these conditions, the piston does not move at all, and a state of equilibrium is said to exist. Now, if one particle of sand is removed, the gas will expand very slightly, but the equilibrium will be restored almost immediately. Such a change is called an infinitesimal change. If the particle of sand is replace, the gas will return to its original volume by the continued removal of the particles of sand. The gas can be allowed to undergo a finite expansion, but each step in this expansion is an infinitesimal one and can be reversed by an infinitesimal change in the external conditions. At all times, the equilibrium is restored immediately. Thus, the necessary condition for reversible compression is that for reversible expansion is. Hence, in general, we can write for a reversible process a process carried out in the above manner is called a reversible process and may be defined as. A reversible process is a process which is carried out infinitesimally slowly so that all changes occurring in the direct process can be exactly reversed and the system remains almost state of equilibrium with the surroundings at every stage of the process. On the other hand, a process which does not meet the above requirements is called irreversible process. In other words, an irreversible process is defined as the process which is not carried slowly. Instead, it is carried out rapidly so that the successive steps of the process cannot be retracted and any change in the external conditions disturbs the equilibrium. The main points of difference between a reversible and an irreversible process may be follows. Reversible process. The process is carried out infinitesimally slowly. Difference between the driving force and the opposing force is very small. At any stage during the process, equilibrium is not disturbed. It takes infinite time for completion. It is only imaginary and cannot be achieved in actual practice. Work obtained in the process is maximum. Irreversible process. This process is not carried out infinite slowly but is carried out rapidly. The distance between the driving force between and the opposite is quite large. Equilibrium may exist only after the completion of the process. It takes a finite time for completion. These processes actually occur in nature. Work obtained in this process is not maximum. Some thermodynamic quantities. A number of thermodynamic quantities appear during the study of thermodynamics. Example: internal energy, heat, work, enthalpy, entropy, free energy, etc. The first three terms are briefly described below. The remaining terms will be discussed at appropriate places. Internal energy. It has already been mentioned that whenever some process, physical or chemical, occurs, it is usually accompanied by some energy change. The energy may appear in different forms such as height, light, work, etc. The evolution or absorption of energy in different processes clearly shows that every substance or the system containing one or more substances must be associated with some definite amount of energy, the actual value of which depends upon the nature of the substance and the conditions of temperature, pressure, volume, and composition. It is the sum of different types of energies associated with atoms and molecules, such as electronic energy, nuclear energy, chemical bond energy, potential energy, and kinetic energy, which is further the sum of the translation energy, vibrational energy, and rotational energy. It is usually represented by the symbol U or E. Thus, the energy thus stored within a substance or a system is called its internal energy. No doubt that every substance or a system is associated with a definite amount of internal energy, but it is possible to find the absolute value because it involves certain quantities which cannot be measured. However, fortunately, it is not required to know the absolute value of internal energy possessed by any system or substance. What is required in different processes is simply the change of internal energy when the reactants change into products or when a system changes from initial state to the final state. This is easily measurable and is represented by internal energy change. If the internal energy of the system in the initial state is Ui and is in the final state it is U2, then the change of internal energy may be given by. Similarly, in a chemical reaction, if UR is the internal energy of the reactants and UP is the internal energy of the products, then energy change accompanying the reaction would be. The internal energy of a system changes when heat passes in or out of the system, work is done or on the by the system, matter enters or leaves the system. Internal energy as a state function. Internal energy as a state function depends only upon the state of system, conditions of temperature, pressure, etc., and it is independent of the method by which the state has been attained. For example, 1 mole of CO2 and 300 Kelvin and 1 atmospheric pressure will always have the same internal energy, irrespective of the fact that it has been brought to these conditions from 500 K and 5 atmospheric pressure or from 1000 Kelvin and 10 atmospheric pressure. That internal energy is a state function may be further explained as follows. Consider a system containing certain amount of water in a thermos flask or in an insulated beaker. Let us change the internal energy of the system by doing work called adiabatic work. This can be done in the following two ways. By doing electrical work, say 1 by rotating a set of small paddles, by doing electric work again with the help of an immersion rod. In each case, temperature is found to rise by the same value, say from T1 to T2. Thus, the same amount of work done, irrespective of the fact that how it was done, produces the same change in state as measurement terms of temperature change. Hence, we write sign of. Two more important points about the internal energy are as follows. The internal energy depends upon the quantity of the substance contained in the system, hence an extensive property. The internal energy of ideal gases is a function of temperature only, hence as isothermal processes as the temperature remains constant, there is no change in internal energy. Work. As learnt from lessons in physics, work is said to have been done whether the point application of a force is displaced in the direction of the force, if F is the magnitude of the force, and the displacement of the point of application in the direction in which the force acts and the work done given by. The above type of work is called mechanical work. However, there are many other forms of work in each of these forms. The electrical work. The generalized force is the EMF, and the generalized displacement quantity of electricity flowing through the circuit. Hence, electrical work done is equal to EMF into quantity of electricity. This type of work is involved in the case of reactions involving ions. Work of expansion, compression, or pressure volume work. This type of work is involved in systems consisting of gases. This is the most important form of work used in the study of thermodynamics. It is the work done when the gas expands or contracts against the external pressure, usually the atmospheric pressure. It is a kind of mechanical work. The expression for such a work may be derived as follows. Here the complete derivation, you can see this. Difference in the work done in reversible expansion and irreversible expansion. In the reversible expansion of a gas, the external pressure is only infinitesimally less than the internal pressure at each stage. Hence, the expression for the work done can be taken as. This equation is further modified to the form given above. In the irreversible expansion, internal pressure is much different from external pressure. For example, if internal pressure is much greater than the external pressure, then as the expansion takes place against external pressure irreversibly, the work done will be given by, for the same change in volume, the work done isothermally and reversibly and the work done isothermally but irreversibly may be represented on the pressure volume diagram as shown in figure 6.7. You can look at the figure 6.7. The area under the isotherm, area AB V1 V2, represent the work done reversibly. The area under the isotherm BC V1 V2 represents work done irreversibly. Thus, for the same increase in volume, work done reversibly is greater than work done irreversibly. Note that in the irreversible expansion, external pressure remains constant, but in irreversible expansion, external pressure has to be decreased continuously so as to remain infinitesimally smaller than the internal pressure. Why a smooth curve of the type AB is obtained for an isothermal reversible expansion. Suppose the external pressure is not constant and is changed in a number of finite steps. Work done by the gas will be summed over all the steps and will be equal to. Look at in the figure 6.8a. If pressure is not constant but is changed in an infinite number of steps, reversible conditions, the different steps will be so continuous that they will give the smooth curve AB. Look at in the figure 6.8. Reversible work of expansion is the maximum work. For reversible expansion should be infinitesimally smaller than, in other words, is the maximum possible value of the pressure, because if pressure is greater than this value, no expansion can occur. Similarly, it can be explained that the irreversible work of compression is the minimum work. Free expansion of an ideal gas, that is expansion against vacuum. If an ideal gas expands against vacuum, the irreversible expansion is called free expansion. Therefore, reversible as well as reversible expansion. Heat. Just as work is a form of energy which is exchanged between the system and the surrounding as the result of expansion or contraction of the gas because of the difference in the internal pressure of the gas and the normal pressure. Similarly, heat is another mode of energy exchange between the system and the surrounding, result of the difference of temperature between them. It is usually represented by the letter Q, small q. It may be pointed out that both heat and work appear only at the boundary of the system. Sign of Q. When heat is given by the system to the surrounding, it is given a negative sign. When heat is observed by the system from the surrounding, it is given a positive sign. Units of Q. Heat is usually measured in terms of calories. A calorie is defined as the quantity of required to raise the temperature of 1 gram of water through 1 degree Celsius in the vicinity of 15 degrees Celsius. In the SI system, heat is expressed in terms of joules. The two types of units are related to each other. It may be noted that whereas internal energy is a state function, work and heat are not state functions of their values do not depend merely on the initial and final states but depend upon the path followed. Work and heat are not state functions. Unlike internal energy, the work done during a process does and merely on the initial and the final states of the system, but it depends upon the path followed. Work is not a state function but a path function. This may be made clear as follows. Suppose we wish to change the from A to B. This may be done showing different paths as shown, confining ourselves to the expansion only. We know that for small change is the pressure, thus the total work of PdV terms, and this to the area under the diagrams. Look at in the figure 6.9 different paths followed in the going from state A to B. It is obvious that areas under the curve are different and hence the work done is when different paths are followed. Heat is not a state function follows directly from the mathematical formulation of the first law of discussed in the next section. It is state function but W is not a state function, hence Q is also not a state function. Law of thermodynamics. First law of thermodynamics is simply the law of conservation of energy, which states that energy can neither be created nor be destroyed. The total energy of the universe, the system and the surrounding remains constant, although it may undergo transformation from one form to other. The energy of an isolated system is constant. Electrical work. The generalized force is the EMF and the generalized displacement quantity of electricity flowing through the circuit. Hence, electrical work done is equal to EMF into quantity of electricity. This type of work is involved in the case of reactions involving ions. Work of expansion, compression or pressure volume work. This type of work is involved in systems consisting of gases. This is the most important form of work used in the study of thermodynamics. It is the work done when the gas expands or contracts against the external pressure, usually the atmospheric pressure. It is a kind of mechanical work. The expression for such a work may be derived as follows. Here the complete derivation, you can see this. Difference in the work done in reversible expansion and irreversible expansion. In the irreversible expansion of a gas, the external pressure is only infinitesimally less than the internal pressure at each stage. Hence, the expression for the work done can be taken as. This equation is further modified to the form given above. In the irreversible expansion, internal pressure is much different from external pressure. For example, if internal pressure is much greater than the external pressure, then as the expansion takes place against external pressure irreversibly, the work done will be given by, for the same change in volume, the work done isothermally and reversibly and the work done isothermally but irreversibly may be represented on the pressure volume diagram as shown in figure 6.7. You can look at the figure 6.7. The area under the isotherm, area AB V1 V2 represent the work done reversibly. The area under the isotherm BC V1 V2 represents work done irreversibly. Thus, for the same increase in volume, work done reversibly is greater than work done irreversibly. Note that in the irreversible expansion, external pressure remains constant, but in irreversible expansion, external pressure has to be decreased continuously so as to remain infinitesimally smaller than the internal pressure. Why a smooth curve of the type AB is obtained for an isothermal reversible expansion. Suppose the external pressure is not constant and is changed in a number of finite steps. Work done by the gas will be summed over all the steps and will be equal to. Look at in the figure 6.8a. If pressure is not constant but is changed in an infinite number of steps, reversible conditions, the different steps will be so continuous that they will give the smooth curve AB. Look at in the figure 6.8. Reversible work of expansion is the maximum work. For reversible expansion should be infinitesimally smaller than, in other words, is the maximum possible value of the pressure, because if pressure is greater than this value, no expansion can occur. Similarly, it can be explained that the irreversible work of compression is the minimum work. Free expansion of an ideal gas, that is expansion against vacuum. If an ideal gas expands against vacuum, the irreversible expansion is called free expansion. Therefore, reversible as well as reversible expansion. Heat. Just Just as work is a form of energy which is exchanged between the system and the surrounding as the result of expansion or contraction of the gas because of the difference in the internal pressure of the gas and the normal pressure. Similarly, heat is another mode of energy exchange between the system and the surrounding result of the difference of temperature between them. It is usually represented by the letter Q, small q. It may be pointed out that both heat and work appear only at the boundary of the system. Sign of Q. When heat is given by the system to the surrounding, it is given a negative sign. When heat is observed by the system from the surrounding, it is given a positive sign. Units of Q. Heat is usually measured in terms of calories. A calorie is defined as the quantity of required to raise the temperature of 1 gram of water through 1 degree Celsius in the vicinity of 15 degrees Celsius. In the SI system, heat is expressed in terms of joules. The two types of units are related to each other. It may be noted that whereas internal energy is a state function, work and heat are not state functions of their values do not depend merely on the initial and final states but depend upon the path followed. Work and heat are not state functions. Unlike internal energy, the work done during a process does end merely on the initial and the final states of the system, but it depends upon the path followed. Work is not a state function but a path function. This may be made clear as follows. Suppose we wish to change the from A to B. This may be done showing different paths as shown, confining ourselves to the expansion only. We know that for small change is the pressure, thus the total work of PdV terms, and this to the area under the diagrams. Look at in the figure 6.9 different paths followed in the going from state A to B. It is obvious that areas under the curve are different and hence the work done is when different paths are followed. Heat is not a state function follows directly from the mathematical formulation of the first law of discussed in the next section. It is state function but W is not a state function, hence Q is also not a state function. Law of thermodynamics. First law of thermodynamics is simply the law of conservation of energy which states that energy can neither be created nor be destroyed. The total energy of the universe, the system and the surrounding remains constant although it may undergo transformation from one form to the other. The energy of an isolated system is constant. Justification for the first law of thermodynamics. This law is purely a result of experience. These is no theoretical proof for it. However, some of the following observations support the validity of this law. Whenever a certain quantity of some form of energy disappears, an exactly equivalent amount, some other form of energy must be produced. For example, in the operation of an electrical fan, the electrical energy which is consumed is converted into mechanical work which moves the blades. The electrical energy supplied to a heater is converted into heat, whereas electrical energy passing through the filament of a bulb is converted into light. Water can be decomposed by an electric current into gaseous hydrogen and oxygen. It is for that 285.8 kilojoule of electrical energy is used to decompose 1 mole of water. This energy must have been stored in hydrogen and oxygen, since same amount of energy in the form of heat is released when 1 mole of water liquid is obtained from gases hydrogen and oxygen. Thus, 285.8 kilojoule of electrical energy which was supplied to the system substance under observations has been recovered later as heat energy. Electrical energy supplied is equal to heat energy produced. Thus, energy is conserved in one form or the other through one form of energy may change into other form. It is impossible to construct a perpetual motion machine which would produce with continuously without consuming energy. There is an exact equivalence between heat and mechanical work. For every 4.814 joules of done, 1 calorie of heat is produced and vice versa. Joule 1840. The above three observations are also sometimes taken as alternate statements of first law thermodynamics, mathematical formulation of the first law of thermodynamics, relationship between infinite energy, work and heat. The internal energy of a system can be increased in two ways. Look at in the figure 6.10, increasing internal energy by absorption of heat and by doing work on the system. Suppose the internal energy of the system U1, if it observes heat Q, its internal energy will become U1 plus Q. If further work W is done on the system, the initial energy will further increase and become U1 plus Q plus W. Let us call this final internal energy as U2. This equation is the mathematical formulation of the first law of thermodynamics. If the work done is the work of expansion, then W is equal to M minus P delta V, where delta P is the change in volume and P is the external pressure. Equation can be written as you can say this. Two interesting results follow from the mathematical formulation of the first law of thermodynamics as under. Neither Q nor W is a state function, yet the quantity Q plus W is equal to delta V is a state function because delta U is a state function. Internal energy U of an ideal gas is a function of temperature. Hence, for ideal gas undergoing an isothermal change, delta U is equal to 0. Hence, Q is equal to minus W. That is, the heat absorbed by the system is equal to the work done by the system. Summing up some important results, you can read this and formulas and units based. Here are some problem practice questions. Anathalpy, another useful state function. The term internal energy has already been explained. Another important aspect, definition of energy change follows from the first law of thermodynamics, according to which if the process is carried out at constant volume, delta V is equal to 0. The above equation then reduces to when subscript V indicates constant volume, hence internal energy change is the heat observed or evolved at constant volume. It may be mentioned further that delta U is a state function, therefore QV is also a state function. It is a process is carried out at constant pressure. As is usually the case because most of the reaction in vessels open the atmosphere, or if a system consists of a gas confined in a cylinder filter, the external pressure acting on the piston in the atmospheric pressure. The work of expansion. V is the increase in the volume and P is the constant pressure. According to the first law of thermodynamics, we know that where Q is the heat observed by the system, delta U is the universe increase in internal energy of the system, and W is the work done by the system. Here the complete derivation, you can see this. Enthalpy change of a system is equal to the heat observed or evolved by the system at constant pressure. It may be remembered that as most of the reactions are carried out at constant pressure in the vessels, the measured value of the heat evolved or observed is the enthalpy change. Further putting the value of Qp from equation we get enthalpy change. Accompanying a process may also be defined as the sum of the increase in internal energy of the system and the pressure volume work done, the work of expansion. Physical concept of enthalpy or heat content. In the above discussion, the enthalpy has been defined, the mathematical expression. Let us try to understand what this quantity really is. It has been described earlier that every substance or system has some definite energy stored in it, the internal energy. This energy may be of many kinds. The energy stored within the substance or the system that is available for conversion into heat is called the heat content or enthalpy of the system of the substance. Like internal energy, the absolute value of the heat content or enthalpy of a system it may be measured, and fortunately this is not required also. In the thermodynamic processes, we are learned only with the changes in enthalpy delta H, which can be easily measured experimentally. Further, it mentioned here that as U and V are extensive properties, therefore the enthalpy is also an extensive property. Exothermic and endothermic reactions. These are those reactions which are accompanied by the evolution of heat. The quantity of heat produced is shown along with the produces with a plus sign. A few examples of endothermic reactions are given below. You can see this. Endothermic reactions. Those reactions in which heat is observed are called endothermic reactions. Although the heat observed can be returned with a plus sign along with the reactants, however, it is usually on along with the products with a minus sign. A few examples of endothermic reactions are given below. You can see this. Exothermic and endothermic reactions in term of delta H. The enthalpy change delta H accompanying action is given by delta H is equal to heat content of products minus heat content of reactants Hp minus Hr. A reaction is exothermic, that is heat is given out in a reaction if the total heat content of the reactants is more than that of the products. But if it is so, then according to the above equation, delta H will be negative. Hence, delta H is negative for exothermic reactions. Thus, the exothermic reactions given above may be written in terms of delta H as examples. You can see this. A reaction is endothermic, that is, heat is observed in a reaction if the total heat content of reactants less than that of the products. Then, according to the equation, delta H is equal to Hp minus Hr. Delta H will be positive. Hence, delta H is positive for endothermic reactions. Thus, the endothermic reactions given earlier may be written in the terms of delta Hs. Graphically, the exothermic and endothermic reactions may be represented as shown in figure 6. The branch of chemistry which deals with the heat and changes accompanying chemical reaction is called thermochemistry. You can look at in the figure 6.14 A exothermic reaction, B endothermic reactions. 6 point thermochemical equations. When a balanced chemical equation not only indicates the quantities of the different reactant and product but also indicates the amount of heat evolved or absorbed as in the above reactions, it is called a thermochemical equation. However, contrary to the usual practice above, the balance equations fractional coefficients used in writing a thermochemical equation. For example, the formation of water is written as thus 285.8 kilojoule of heat is produced when 1 mole of hydrogen reacts with 0.5 mole of oxygen. Quantities of reactants are doubled. The heat produced will also be doubled. For example, in the above we may write some conventions about thermochemical equations. For exothermic reactions, delta H is negative, whereas for endothermic reactions, delta H is positive. Unless otherwise mentioned, delta H values are for the standard state of the substances. The coefficients of different substances represent the number of moles reacted and formed for the heat change represented in the equation. The physical state of the different substances must be mentioned as the heat evolved or observed depends upon the physical state as discussed in the next section. If the coefficients of the substances are multiplied or divided by some number, the value of delta H is multiplied or divided by the same number. If the reaction is reversed, the sign of delta H changes but the magnitude remains the same. Heat of reaction or enthalpy of reaction or enthalpy change of reaction. The amount of heat evolved or observed in a chemical reaction when the number of moles of like reactants as represented by the chemical equation have completely reacted is called the amount of reaction or enthalpy of reaction or enthalpy change of reaction. It is represented by delta RH. Let us consider the following two examples. You can look the reactions. The first equation indicates that when 1 mole of methane combines completely with 2 moles of gas of heat is produced. Similarly, the second equation tells that when 1 mole of solid reacts completely with 1 mole of steam, kilojoule of heat is observed. It is interesting to note that enthalpy of reaction delta H is equal to sum of enthalpies of product minus sum of enthalpies of reactants. Hence, it is essential to write the symbols SLG or to indicate whether a particular substance, solid, liquid, gaseous or an aqueous solution. Allotropic modifications. For elements like sulfur and carbon will exist in different modification, the heat of reaction is different. Different allotropy form is involved in the reaction. Concentration of solution. Heat changes occurs when a solute is dissolved in a solvent solution or when a solution is diluted. Therefore, if the solution are involved in a reaction, concentrations affect the heat of reaction. Temperature. The heat of reaction depends upon the temperature at which the reaction products are taken. The values are usually reported at 298 Kelvin. Conditions of constant pressure or constant volume, whether the reaction take constant pressure or a constant volume. Standard enthalpy of reaction. The enthalpy change of a reaction depends upon the under which the reaction is carried out. Hence, it is essential to specify some standard conditions. The standard enthalpy of a reaction is the enthalpy change accompanying the reaction. All the reactants and products are taken in the standard states. A substance is said to be in the standard state when it is the purest and most stable for pressure and the specified temperature. This temperature is usually taken as 25 degrees Celsius, that is 298 Kelvin. Need not be so always. For example, standard state of pure ethanol at 298 Kelvin is pure liquid ethanol and 1 bar pressure, whereas standard state of iron at 500 Kelvin is pure iron at 500 Kelvin and 1 bar pressure. Note: earlier the standard pressure was taken as 1 atmosphere, but in terms of 1 atmosphere. Thus, conversion of bar into SI units is more, hence IUPAC recommends 1 bar as the standard pressure. The enthalpy change of a reaction is the standard state is represented by the superscript. It is represented as different types of heats, enthalpies of reaction. Heat of reaction or enthalpy of reaction is a general term used for the heat change accompanying any reaction. However, depending upon the nature of the reaction, the enthalpy of reaction is named accordingly. Enthalpy of combustion, similarly, depending upon the type of process involving a phase change. Fusion, variation, sublimation, the enthalpy change involved is named accordingly. A few important heats of reactions are as follows. Enthalpy of combustion. The enthalpy of combustion of a substance is defined as the heat change, usually the heat evolved, when 1 mole of substance is completely burned or oxidized in oxygen. This reaction shows that 890.4 kJ of heat is produced when 1 mole of methane is completely burned. Hence, enthalpy of combustion of methane is 890.4 kJ mole inverse. The significance of the words completely oxidized must be clearly understood. For example, carbon may be oxidized to carbon monoxide or carbon dioxide. The heat evolved in two cases are different. Complete oxidation means oxidation to CO2 and not to CO. Hence, heat of combustion of carbon is standard enthalpy of combustion. It is amount of heat evolved when 1 mole of the substance under conditions 298 Kelvin 1 bar pressure is completely burned to form the products. Also under standard conditions, it is represented by the standard enthalpy of combustion of butane C4H10, the main constituent of cooking gas, representing the combustion of 1 mole of butane, may be represented as follows. Calorific values of foods and fuels. Just as the fuels like coal, kerosene oil, gasoline, petrol, diesel oil, etc. burn to produce energy for the running of machines, similarly for the working of the human machine, we eat carbohydrates, fats, etc. in the form of food. The carbohydrates are first decomposed in our body by the enzymes, form glucose, which then undergoes oxidation by the oxygen that we inhale to produce energy. This oxidation reaction is usually called combustion of food. Different fuels and food produce different amounts of the heat on combustion. These are usually expressed in terms of their calorific values, which is defined as follows. The calorific value of a fuel or food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of the fuel or the food. Thus, according to the above reaction, 1 mole of glucose, that is 180 gram of glucose, produce heat. A normal person needs about 3000 calories per day. The food consisting carbohydrates, oils, fats, vitamins, proteins, minerals, salts, etc., which provides the necessary calories, called a balanced diet. Enthalpy of formation. The enthalpy of formation of a substance is defined as the heat change, heat evolved or observed when 1 mole of the substance is formed from its elements under given condition of temperature and pressure. It is usually represented by delta FH. The conditions of temperature and pressure usually chosen are 298 Kelvin and 1 bar pressure, the called standard state. The enthalpy of formation under these conditions is called standard enthalpy formation. Standard enthalpy of formation of a substance is defined as the enthalpy change accompanying the formation of 1 mole of the substance in the standard state from its elements, also taken in the standard state. Importance of standard enthalpies of formation. Knowing the standard enthalpies of formation of the different compounds involved in a chemical reaction, the standard enthalpy change of the given reaction can be calculated using the formula. You can see the formula. Elementary substances in the standard state, the standard enthalpy of formation is taken as 0. The standard state of elementary substances means the most stable form of that substance at the given temperature, usually 298 Kelvin and 1 bar pressure. It refers to the normal physical state in which it exists under these conditions, and in case of elements showing allotropy, it refers to the most stable allotropy form. For example, the standard states of oxygen, bromine, and iodine are O2, G, Br2, and I2, whereas standard states for carbon and sulfur are C, graphite, and rhombic. For example, you can see the example. Suppose we want to predict the enthalpy of combustion of methane. Enthalpies of formation of different compounds help to predict their relative stabilities. Only those compounds are more stable than their elements whose delta F H naught values are negative. Greater the magnitude of the negative value, more is the energy released, for more stable is the compound. Enthalpy of the neutralization. The enthalpy of neutralization of an acid by a base is defined as the heat change, usually the heat evolved. When 1 gram equivalent of the acid is neutralized by a base, the reaction being carried out in dilute aqueous solution. The enthalpy of neutralization of a base by an acid is defined in a similar manner. For you can see the example. Thus, enthalpy of neutralization is the heat evolved for the reaction between the H positive ions given the acid with the OH negative ions given by the base to form 1 mole of H2O. Since strong acids and strong base ionize completely in dilute aqueous solution, the number of ions and OH negative ions produced by 1 gram equivalent for the strong acid and the strong base is always same. Hence, the enthalpy of neutralization between a strong acid and a strong base is always constant. In case either the acid or the base or both are weak, the enthalpy of neutralization is usually less. The reason for this may be understood by considering the neutralization of a weak acid like acid with a strong base like NaOH. Acetic acid ionizes to a small extent, whereas NaOH ionizes as when H positive ions given by the acid combine with the OH negative ions given by the base, the equilibrium shifts to the right. More of acetic acid dissociates. A part of the heat produced during the combine of H positive and ions and OH negative ions is used up for the complete dissociation of acetic acid. The heat thus used called enthalpy of dissociation or enthalpy of ionization. It is 1.9 kilojoule for the acetic acid. Hence, the heat evolved in the above reaction. The heat of neutralization is taken for 1 gram equivalent of the acid and base. Because the neutralization involves combination of 1 mole of H positive ions and 1 mole of OH negative ions. Enthalpy of solution. The enthalpy of solution of a substance in a particular solvent is defined as the enthalpy change, amount of heat evolved or absorbed when 1 mole of the substance is dissolved a specific amount of the solvent. However, if such a large volume of the solvent is taken, further addition of the solvent does not produce any more heat change. It is called enthalpy solution at infinite dilution. You can see the example. Enthalpy of solution from lattice enthalpy and enthalpy of hydration. The dissociation of their compound in water takes place in the following two steps. Dissociation of the ionic solid into free ions. The energy required for this process is called lattice energy or lattice enthalpy. Hydration of the ions, or in general called solvation of the ions if solvent other than water is the energy released in this process is called hydration energy or enthalpy of hydration. As mentioned above, for most of the ionic compounds, delta solution H is positive. Hence, dissolution of most of the increases with increasing temperature. If the lattice enthalpy of a salt is very high, the dissolution of compound may not take place at all. It is for the reason and that fluorides are less soluble than chlorides. Calculation of lattice's enthalpy from Born-Haber cycle. Lattice enthalpy of an ionic solid compound is enthalpy change that occurs when 1 mole of the ionic compound dissociates into ions in the gases. Fritz Haber in 1919 put forward a method based on Hess law for the calculation of energy and hence for the predicting the stability of the ionic and formed because larger is the negative value for lattice energy, greater is the stability of and formed. This method is known as Born-Haber cycle. It is briefly described below, taking the NaCl. The complete process involving the formation of 1 mole of NaCl directly and through a series of steps indirectly may be represented by a cyclic process as shown in figure 6.15. Look at in the 6.15 figure, applying Hess law, according to which the heat change is same whether 1 mole of the compound is formed directly or indirectly through a number of steps, and using the symbols without proper signs we have. Substituting the values with proper signs, positive sign if energy is absorbed and negative sign if energy is released, we get for the case of NaCl. Thus, lattice enthalpy of NaCl has a large negative value. This explains why the NaCl is highly stable. It may be pointed out that the direct determination of electron affinity is also very difficult. Values have been obtained only for a few elements. Hence, Born-Haber cycle is used for the electron affinity, also using the calculated values of lattice enthalpy from crystal parameters. Two important consequences of lattice enthalpies. Greater the enthalpy, more stable is the ionic compound. Greater the lattice enthalpy of an ionic compound, less it is solubility in water. Enthalpy of atomization: when 1 mole of a given substance dissociates into gaseous atoms, the enthalpy change panning the process is called the enthalpy of atomization. It is represented by the symbol. In the first example, enthalpy of atomization is same as bond dissociation enthalpy. In the third example, enthalpy of atomization is same as enthalpy of sublimation. The second represents only enthalpy of atomization and not bond energy as discussed later. When a covalent compound on dissolution in water splits to produce ions in the solution, enthalpy change accompanying the process is called enthalpy of ionization. For example, of HCl, thus enthalpy of ionization of HCl is negative 75.2 kilojoule mole inverse. In fact, the enthalpy of ion covalent compound is the same as its enthalpy of solution or enthalpy of dissolution. Enthalpy of formation of ions: when an ionic solid is dissolved in water, free ions are the aqueous solution. For the calculation of enthalpy of formation of an ion is in the aqueous solution of formation of H positive ions in the aqueous solution is taken as 0. For example, delta FH for aqueous solution can be calculated from the following data. Enthalpy of hydration. The amount of enthalpy change, the heat evolved or absorbed when 1 mole of the anhydrous salt combines with the required number of moles of water so as to change into the hydrated salt is called the enthalpy of hydration or heat of hydration. Enthalpy of hydrogenation: the amount of enthalpy change that takes place when 1 mole of an unsaturated organic compound is completely hydrogenated is called enthalpy of hydrogenation. 10th, enthalpy of allotropic transformation: the enthalpy change that takes place when 1 mole of one form of allotropy modification changes to other is called enthalpy of allotropic transformation. It is interesting to note that magnitude of enthalpy change represented along with the balance equations is for the number of moles of different reactants reacted and the number of moles of different products formed, yet the units of delta R are always written as kilojoule mole inverse. This is because if an equation is multiplied by a number, the units do not change. Enthalpy changes during phase transitions. Enthalpy of fusion. Enthalpy of fusion is the enthalpy change accompanying the transformation of 1 mole of a substance into its liquid state at its melting point. It is called a molar enthalpy. Example: the molar enthalpy of fusion. Freezing is reverse of fusion. The enthalpy of freezing or enthalpy of solidification has same. Enthalpy of fusion has the opposite side. Thus, you can see this. Enthalpy of vaporization. It is amount of heat required to convert 1 mole of liquid into its vapor state at boiling point. It is also called molar enthalpy of vaporization. For example, the molar enthalpy of vaporization of water into its vapor. Boiling point of water 373 Kelvin is 40 kilojoule. It may be represented as condensation is reverse of vaporization. The enthalpy of condensation has the same value enthalpy of vaporization but the opposite signs. Enthalpy of sublimation. Sublimation is the process in which a solid on heating changes directly into gaseous state but melting point. Enthalpy of sublimation of a substance is the enthalpy change accompanying the conversion of 1 mole of a solid directly into vapor phase at a given temperature below its melting point. For example, the enthalpy of sublimation of iodine. Most solids, the sublimine readily are molecular solids, example iodine, naphthalene, etc. It may be pointed out that sublimation is nothing but fusion and vaporization carried out in. Otherwise, also this equation is true because enthalpy is a sphere property. The magnitude of enthalpy change for a phase transition depends upon the strength of forces. For H2O is much larger than for acetone because the former has hydrogen bonding. Hess law of constant heat summation. G.H. Hess, a Russian chemist in 1840, gave a law about the heats of reactions on the base experimental observation. This law is known after his name, Hess law. It states as follows: the total amount of heat evolved or observed in the reaction in the same whether the reaction takes place in one step or in a number of steps. In other words, the total number of heat change in the reaction depends only upon the nature of the initial reactants and the nature of the final products, and it is independent of the path or the manner by which this change is brought about. Basis of Hess law. Now, Hess law follows from the fact that enthalpy is a state function. Enthalpy changes depends only on the initial state, enthalpy of the reactant and the final state, and does not depend upon the path followed. Example 1: when carbon graphite burns to form carbon dioxide directly in one step. You can see this. Theoretical proof of Hess law in given figure, you can look at this. Applications of Hess law. The most important application of Hess law is the calculate heat changes for the reactions for which experimental determination is not possible. The calculation based upon the following consequence of Hess law. The thermochemical equations can be treated as algebraic equations which can be subtracted, multiplied or divided. A few important applications of Hess law. These are given below. Calculation of enthalpy of formation. The enthalpies of formation of many compounds determined experimentally. These are calculated by the application of Hess law. The following illustrate the method. Here the some sample problem questions. Calculation of enthalpy of allotropic transformation. Elements like carbon and sulfur exist in different allotropic forms. The change of one form to the other involves a very small amount of heat and is a very small process. Hence, the experimental determination of heat changes for such transformations is very difficult. These are calculated by the application of Hess law as illustrated by the example given below. Here some sample problem question. Calculate of the enthalpy of hydration. The experimental determination of the enthalpy of hydration is almost impossible. However, it can be easily calculated using Hess law as illustrated by example. Predicting the enthalpy change for any reaction. Hess law can be applied to predict the enthalpy for any reaction from the enthalpy changes of certain other reactions. The numerical problems below. Bond enthalpy or bond energy. We know that energy is evolved when a bond is formed and energy is required for the dissociation. Hence, bond formed is defined as follow. Bond energy is the amount of energy released when 1 mole of bonds are formed from the atoms in the gaseous state, or the amount of energy required to dissociate 1 mole of present between the atoms in the gaseous molecules. It is represented by diatomic molecules like H2O2, N2Cl2, HCl, HF, etc. The bond energies are equal to their energy. These may called enthalpies of atomization. Polyatomic molecules. The bond energy of a particular bond is not the same when present in bond energy, or particular type of bond is not same even in the same compound. Here the bond enthalpies of some common bonds in figure 6.1 table. You can look it in this. Bond energy usually means bond dissociation energy. Hence, it is always taken as positive because it is the energy required and not the energy released. Further, it is energy 1 mole of particular type of bonds and not for 1 mole of the substance. Difference between bond energy and bond enthalpy. Strictly speaking, bond energy should be delta U values. However, the normally reported values are bond enthalpies values. Bond dissociation energies are obtained at 0 Kelvin by spectroscopic method, whereas bond enthalpies are calculated by considering contributions from heat capacities. For example, bond enthalpy of H2 at 298 Kelvin. the corresponding bond energy for this reaction. Thus, there is very small difference and the two are used interchangeably. An important use of the bond enthalpy is that it helps to calculate the enthalpy of formation of atoms. For example, from the above reaction, calculation of bond enthalpy for polyatomic molecules, the bond enthalpy of a particular bond found from the values of the enthalpies of formation, which is turn may be obtained from the enthalpies. Similarly, the bond enthalpies diametric molecules like HCl, HF, etc. can be obtained directly from experiments or may be calculated from the bond enthalpies of homonuclear diatomic molecules. These calculations are illustrated below in the solved problems given below. You can look at this. Limitations of the first law of thermodynamics, introduction of the second law of thermodynamics. A major limitation of the first law of thermodynamics is that it merely indicates that in any process is an exact equivalence between the various forms of energies involved, but it provides no information the spontaneity or feasibility of the process, whether the process is possible or not. For the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that is that if the process occurred, the heat energy gained by one end would be exactly equal to that loss the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can run euphil, etc. The answers to the above questions are provided by the second law of thermodynamics. However, we take up different statements of the second law of thermodynamics as given in section 6.20. It is important to know that we understand by a spontaneous process and also introduce two more thermodynamic quantities, namely entropy and Gibbs free energy. Spontaneous and non-spontaneous process. To understand what I mean by spontaneous process, let us consider the following two processes: dissolution of sugar in water at room temperature 25 degrees Celsius, burning of coal in air or oxygen. The process takes place by itself, although it may be slow. The second process cannot be placed by itself. It needs an initiation. We have to bring a flame near the coal to start its burning. But once it starts burning, it goes on by itself without the help of any external agency. Both the above processes are spontaneous process. Hence, a spontaneous process may be defined as follows: a process which under some given conditions may take place by itself or by initiation independent of the rate is called a spontaneous process. In other words, a process which can take place by itself or has an urge or a tendency to take place is called spontaneous process. Or sum up, a spontaneous process is simply a process which is feasible. It may be noted carefully that a spontaneous process does not mean that the process should instantaneous. In fact, the rate of process may vary from extremely slow to extremely fast. For a more clear understanding, a few more examples of spontaneous processes are as follows. Example of processes which take place by themselves: dissolution of common salt in water, evaporation of water in an open vessel, flow of heat from heat end to cold end, or from a hot body to a cold body. Example, cooling down of a tea. Flow of water down a hill, combination of nitric oxide and oxygen to form nitrogen dioxide, combination of H2 and IO2 to form HI. Examples of processes which take place on initiation: lighting of a candle involving burning of a wax, heating of a calcium carbonate to give calcium oxide and carbon dioxide indicated by heat, combination of hydrogen and oxygen to form water when initiated by passing an electric reaction between methane and oxygen to form carbon dioxide and water. A process which can neither take place by itself nor by initiation is called a non-spontaneous process. A few examples of non-spontaneous process in everyday life: flow of water up a hill, flow of heat from a cold body to a hot body, diffusion of gas from low pressure to high pressure, dissolution of sand in water. The driving force for a spontaneous process. After having learned that we have a spontaneous process, the next question that arises in our mind is why some processes are spontaneous. Obviously, there must be a force which drives the process or a reaction in a particular direction. This force, which is responsible for the spontaneity of a process, is called the driving forces. Tendency for minimum energy. It is a common observation that in order to acquire maximum stability, even every system tends to have minimum energy. For example, A stone lying at a height has a tendency to fall down so as to have minimum potential energy. Water flows down a hill to have minimum energy. A wound watch spring has tendency to unwind itself to decrease its energy to minimum. Heat flows from hot body to cold body so that heat content of the hot body becomes minimum. Thus, all the above processes are spontaneous because they have a tendency to acquire minimum. Again, let us consider the following reactions. You can see this. All these reactions are accompanied by evolving heat. In other words, the heat content of the product is less than those of the reactants. Thus, again, we may conclude that these reactions are spontaneous because they are accompanied by decrease of energy. Effect of temperature on the spontaneity of a process. The spontaneity of a process depends upon the energy factor, the randomness, entropy factor. The magnitude of the first factor does not change with much temperature, but the second factor changes applicably with change of temperature. Hence, the resultant delta G is equal to delta H minus T delta H. Food should be temperature, and so would be spontaneity of the process. For endothermic reactions, delta H is always positive. This factor opposes the process. If T delta S is negative, this factor will also oppose the process, and process will be non-spontaneous. However, then the process can occur if magnitude of the temperature T delta S is greater than the magnitude of delta H. The reaction is said to be entropy driven. The magnitude of the factor T delta S is affected by temperature as follows. If the temperature is very low such that in magnitude delta G will be positive and hence process will be non-spontaneous. If the temperature is moderate such that slightly is magnitude delta G will be slightly negative, hence the process will be spontaneous but slow. If the temperature is high, T delta S will be much greater than delta H is magnitude, so that delta G is higher negative, hence this process will not only be spontaneous but first thus. An endothermic reaction which may be non-spontaneous at low temperature may become spontaneous at high temperature. B. For exothermic reactions, delta H is always negative. This factor always favors the process, that is T delta S is positive. This factor will also favor the process and the process will always be spontaneous. This reaction is said to be enthalpy driven. The magnitude and hence the spontaneity of the reaction is affected by the temperature as follows. If the temperature is so high in magnitude, delta G will be positive and the process be non-spontaneous. If the temperature is made so low that T delta S delta H is magnitude, delta G will be negative. An exothermic reaction which may be non-spontaneous at high temperature may become spontaneous at low temperature. You can look in the given table 6.3 effect of sign delta H and delta S temperature on the spontaneity of the process. Here are the examples. Standard free energy change of a reaction. Standard free energy change of a reaction is defined as the change in free energy which take place when the reactants in the standard state are converted into the products in their standard state. Just as the enthalpy of a reaction can be calculated from the standard enthalpies of formation, the standard enthalpies of formation of the elements as zero. Similarly, the free energy change during a process can be calculated from the standard free energy of formation of the different reactants and products involved, taking standard free energy of formation of the elements as zero. Standard free energy of formation of compound is defined as the free energy change which takes place when 1 mole of the compound is formed from its element taken in the standard states. Standards free energies for formation of same compound in kilojoule mole inverse at 298 Kelvin. You can look it in this given table. The standard free energies of formation of few solid, liquid and gaseous compounds are given in the below. You can look at this.